So we've just finished confidence intervals for proportions, and our next topic here is confidence intervals for means. So recall our general form for all confidence intervals. We have a statistic, plus and minus, a margin of error, where the margin of error is some multiplier times the standard error, and the multiplier is determined by the distribution of the statistic. So our statistic that estimates mu, the population mean is x bar, the sample mean. So that we would put that in for our statistic. The standard error is sigma over the square root of n, so we could put that in. And because the sample mean is normally distributed, the multiplier would be z star. But there's a problem. What is sigma? It's the standard deviation, but what kind of standard deviation? It's the population standard deviation. So if we don't know mu, the true population mean, then how do we know sigma, the true population standard deviation? And the answer is we don't know. We don't know what sigma is. So in statistics, when we don't know something, we just move on to plan B, which is to estimate it with the sample quantity. In this case, estimate sigma with S, the sample standard deviation. So that's a good plan, but now that presents another problem. And that is that we have two estimates, sample mean and sample standard deviation. Both of these are not going to be exactly equal to the true value. And so that means that we have two sources of random error in our problem. The normal distribution, i.e. z star, as our multiplier of the standard error, only accounts for the random error from estimating mu, the population mean, with x bar, the sample mean. So if the normal distribution can't quite get it done, we're going to call on the cousin of the normal distribution, the t-distribution. Is the shorter, fatter cousin of the normal distribution. So in this plot up here, this graph, the black line at the top is the normal distribution, and all these red lines are actually t-distributions. So the cousins, it's a whole family of cousins. The thing the whole family has in common is that they're all centered at 0. They're all bell-shaped, and they're all symmetric. Where the t-distribution differs from the normal is that it's wider. It's shorter and wider, thicker tails. So it's literally like if you took your hand and you pressed down on top of the normal. So if you press down on it, and some of it would come squishing out the sides. Okay, so that's exactly what's happening. They all have 100% area under the curve. But as I just said, the t is wider, more variability. Okay, and it's this added variability that's going to account for that second source of random error. So the t-distribution is used because we are also estimating the standard deviation, and the added variability in the t-distribution takes into account the added random error caused by estimating two quantities the mean and the standard deviation. So another big difference between the normal and the t-distribution is that the t is a family of distributions. There's only one normal distribution, but as you can see, there's many of these red lines. And these are just some examples of the t-distribution. There's many, many more. Which t-distribution to use is determined by the degrees of freedom for S, the sample standard deviation. So way back at the beginning of the semester, we talked about how the degrees of freedom for the sample standard deviation was n minus 1, and dividing by n minus 1 in our estimate gave us a better estimate of the population standard deviation. So what our degrees of freedom for S is what's going to determine which t to use. So putting that all together, our confidence interval formula for sample means is going to be x bar plus or minus t star instead of z star and S over the square root of n for the standard error. Okay, so let's so these calculations are pretty much exactly like what we did when we looked at the central limit theorem problems, except for this one difference here of using t star instead of z star. So let's first concentrate a little bit on just how we find t star. So let's look at a couple of examples that I have down here. So let's suppose in example 1 that the sample size is 9 and our confidence level is 80%. Our degrees of freedom are going to be 8. Okay, and we'll look that up on the table in a second. And at the same time, let's look up also if we have sample size of 20 and we want a confidence level of 95% for a 95% confidence interval. Our degrees of freedom are going to be 20 minus 1 or 19. And I maybe should have written that up here. That 8 is coming from 9 minus 1. Okay, so in the back of your, on the pages immediately preceding the normal distribution, so this is both in the orange book and the blue book, is a t-table. And I think you're going to find that this is much easier to use than the normal table. On this table, each row represents one t-distribution. Okay, remember there's many, many t-distributions. So for each t-distribution, we have only like 1, 2, 3, 4, 5, 6 different values. So instead of 2 pages of values, we only have 6. And so they give us the most popular ones. So for confidence levels, we have the 80%, 90%, 95, 98, 99, and 99.9. So how we use this is, so for example, if we have, so the confidence levels go across the top, and down the vertical edge are the degrees of freedom. So that's what this DF is. So we had a sample size of 9, which gave us a degrees of freedom of 8, which means that our T star would be 1.397. So notice that in this column, that's the 50% mark, and those are all zeros. And then in the column on the other side, this is all infinities because the tails never touch. We never can have 100% confidence. Okay, in our second example, we had n was 20 which meant our degrees of freedom were 19, and we wanted a 95% confidence interval, which will give us a t-star of 2.093. Okay, let's look at a couple more examples. Let's say in this third example that we have a sample size of 38 and we want a 90-degree confidence level, and in the next one 350 and a 99% confidence level. So for n equals 38, our degrees of freedom are going to be 38 minus 1, or 37. And for 350 minus 1 is 349. Okay, so to find those, we have to go to the next page. And so we're going along here, 28, 29, 30, 30, 40. Okay, notice all of a sudden the table started jumping by tens. And then it's going to jump by 20s, and then eventually by 200. So you might think that, well, if we have 37 degrees of freedom, that we would, just go to 40 because that's closer. But we're going to have to always round down. Because if we went to 40, that would be like saying, oh, well, we had 41 observations when we don't. That would be like claiming we have more data than we actually have, and we would consider that to be unethical. For 349 degrees of freedom, and did I say 99% confidence interval, we would have to use 200, which would give us a t-star of 2.601. But a couple things to note. The reason the table starts jumping is because these numbers start getting so close together. Remember, they all lie underneath the normal. Normal's the tallest one. And as the degrees of freedom get larger and larger, that t-distribution is getting closer and closer and closer to the normal till they're really squeezed in there. Like, there's just not much difference between 2.601 and 2.588. In WebAssign, it may detect the difference or it may not. And also, there are like a lot of online apps for finding t-star or values from the t-distribution. If you did it exactly, you're going to find a value in between one of those, and some of your calculators might do that as well. So notice, for example, our 99% or 95, our old favorite, 1.96. Well, at 5,000 degrees of freedom, it's so close to the normal that it is 1.960. At 2,000, it's 1.961, 62, 63. Notice how close all of these are. Okay, and what's along the bottom here is infinity. Well, of course, we're never going to have degrees of freedom n minus 1 equal infinity. But this is kind of here like as a reference, so you can see just how close these values are getting to the normal. So these are actually the values from the normal distribution. So these are actually the z-star values. So notice there's our 1.96 that we've seen so many times, 1.645. So this is actually a shortcut that you can use when you need to find z star values for a different kind of problem. So let's make a note here about these larger degrees of freedom. Always round down on the degree when using the t-table, because otherwise it is like claiming you have more data than you actually do. And I want to bring your attention to this important little note here about sample size. Okay, so we're still using the central limit theorem. Everything we're doing for the whole semester is based on that. So when we talked about what sample size we need to use the central limit theorem, like that still applies here. So if the population is normally distributed, any sample size is okay. If there are no outliers, then we can assume 15 is large enough. And if there are outliers, then we're going to need 40. So here, like on these first couple examples, like on this one, it would have to be from a normal population. And for these two, it would have to be no outliers in the sample. So the next example is kind of very appropriate for what we're going through right now. And that the data from this example comes from this article in the Annals of Emergency Medicine called Drive-Through Medicine. And it is entitled like a novel proposal for rapid evaluations of patients during an influenza pandemic. So the idea that they're going to test here is the idea of drive-through flu testing. So this came from a pandemic scare in 2009 with H1N1, which never actually turned into a pandemic on the scale of what we're seeing with the coronavirus. And this article is talking about what would happen with an influenza pandemic. I think what we're seeing now with a coronavirus pandemic is worse than what they had envisioned. But we'll see that there's a lot of what they pioneered here is actually being used today. So their idea was, instead of having these flu patients go into the emergency room and thereby exposing all the people in the emergency room to the flu, that they would instead do drive-through. So people would drive in, there'd be a parking lot where they would park and wait their turn, then they would go in, there's two lanes they could go down, registration, triage, observation and dispensing pharmacy, and discharge. So, at the beginning here, there's somebody here saying, hey, do you have flu symptoms? If you do, you go in here. Otherwise, you go to the regular emergency department. So they had 38 patients that they tested this on. And these were not real patients. What they did is that they actually took the charts from 38 patients who had gone to the emergency room, and they had actors duplicate the symptoms and what those patients had told the doctors. So these were actors playing the charts of real patients. So what they found from this experiment is that they were able to do this with the sample mean length of stay from the time that they enter down the flu into the flu parking lot till the time they're discharged. The sample mean was 26 minutes with a standard deviation of 1.57 minutes. For purposes of this problem, we're going to assume that there were no outliers. And let's say we want to find a 95% confidence interval for the true mean length of time that it's going to take somebody to go through this flu testing station. So our givens are, we have an N of 38, X bar is 26, sample standard deviation of 1.57. Our degrees of freedom are going to be N minus 1 or 37. And from the t-table, we're going to use degrees of freedom 30 because we always round down. And this is going to give us a t star of 2.042. And so at that point, we have everything we need. We plug in x, t star, s over the square root of n, and it gives us this. And so at this point, we just need to put it into our calculator. That's going to give us 26 plus or minus 0.052. So this 0.52, that is the margin of error. Oh, I have that written right here. And subtracting that from 26 gives us 25.48. Adding it gives us 26.52. So our confidence interval for the true mean, we're 95% confident that the true mean is between 25.48 and 26.52. Okay, so again, 95% confident that that's where the true mean value is. And we know that because 95% of all possible samples will produce a 95% confidence interval, which captures the true mean. And we know that from the central limit theorem. Okay, so again, I want to impress upon you that this is saying where we think the mean is. It's not saying that 95% of all the patients were there in this little narrow band of time. So our distribution of our sample looks something like this, with 26 at the middle, and then one standard deviation is 1.57. And now our confidence interval is just like right around like where the mean is. Okay. And for some reason, confidence intervals for means are much more prone to misinterpretation than the ones for proportions. So common misinterpretations. The first one is to say that 95% of all patients had a length of stay in that interval. Okay, and that's what we were just talking about. That's false because this statement is being made about the whole population. And the confidence interval is making a statement about where the mean of the population is. So just as a little side note here, if the population was normally distributed with a mean of 26 and a standard deviation of 0.57, this would be back from like what we did on the first test. We would expect that 95% of the population to be between 22.92 and 29.08. So notice how much larger than the confidence interval for the mean that is. A second misinterpretation is along the same lines, would be to say something like 95% of the time a patient will wait in that interval. Okay, so yeah, again, just that's not saying that 95% of the patients are going to wait almost exactly 26 minutes. No, they're going to be much more spread out. That's, again, where the mean is. Third misinterpretation is to say there's a 95% probability that the true mean is in that range. And that's what we talked about at length with the confidence intervals for proportions. We don't use the word probability because the parameter, the true value, is one set value. We don't know what it is, but it's not moving around. When we talk about probability, that would assume that the true value was moving around. Okay, so there's no probability. That's why we say we're 95% confident. Oh, this next one, another misinterpretation, is to say we're 95% confident the sample mean is between those two values. Well, no, the sample mean is 26. It's at the center of the interval. We're 95% confident that the true mean is in that value, not the sample mean. Or something like 95% of all sample means will be in that range, okay? So that's false because the central limit theorem tells us where sample means are relative to the true mean, not where sample means are relative to other sample means. Okay? Yeah, so to say this would be like saying, making that leap that the true mean is 26, when we don't know that. That's just an estimate. So just a couple little things to add on to this. As soon as this pandemic started, I thought immediately of this example that was in the book about the drive-through clinic that was tested out 10 years ago. And sure enough, like right away I saw drive-through testing in South Korea, and now it's sprung up. It's all over the United States. We have a drive-through test site in South Portland, possibly other ones, I'm not sure. This is just what I found from a quick Google. But I also read a really sad article in the New York Times today, which was about some scammers who set up a drive-through test, and they were just gathering like $240 per, I don't want to say patient, per person that they conned, and they were like swabbing them, and they weren't even changing their gloves out in between doing this. So really sad that they could have actually been spreading it to these poor people who wanted to be tested. So be careful. Crisis brings out the best in people, and sadly sometimes it brings out the worst in people. And then a little reality check on this data. I said for purposes of this example to assume there were no outliers. And if you look at the actual data, it looks like there's a couple weird values, like patient 20 I guess, and 21. One of them is really low, one of them is really high. Given they're right next to each other, I kind of almost wonder if some of those times were wrong. Like this one was actually supposed to be a little longer, and this one was supposed to be a little shorter, that they timed them a little bit wrong. Also notice it's not really quite like a random sample because they seem to be getting a little bit faster at it as they're going along. Although these, towards the second half of the data, that's when the parking lot was actually full. So there was more wait in the parking lot time, but they were actually doing a little bit better at getting people through faster. So we made a few simplifications in our calculations. The actual data might have been a little bit more complex. Okay, so I am planning to do another example on Wednesday, but I'm pretty much done with confidence intervals for means except for one more example. And so I think at this point you can go ahead and do in-class exercise 17. That's on pages 54 and 55. And I'm going to go ahead and post this assignment, and I will make it due Tuesday, April 13th.